cataract and the areas that have been stripped of less, so the areas affected by the floods. This is pre-LiDAR days. This is a 20-meter resolution DEM. We were at the visitor center on the edge here, same area that's on the LiDAR, but you see more of it here. So this is the width of the flow. We drove, basically climbed this way, so you were looking at this area. What you also may have noticed is the landscape here has totally changed. We're out of the basalt. We're not seeing the basalt. It's below us. We're in the cover of mostly less, not just less though, but the glacial things, glacial materials, because we are now technically under what would have been the Okanagan lobe. So the margin of the Okanagan lobe is sort of visible on the old DEMs, but much better, more visible on the LiDAR ones today, and we'll talk about those in a second. We crossed one of the moraines of the Okanagan lobe. So we'll use the word, the concept is often in the literature of the Withrow moraine. When you think of the Withrow moraine, think more of it as a zone, right? It's the terminal zone of the glacier. It's not a single feature or a single ridge, despite what the textbook diagrams will show you about a moraine being this pile of material. It's a zone. It's a zone. The Withrow moraine that most people refer to, the zone in question, is here where we're going after. The Withrow moraine is this area in Moses Coulee, it's the portion of Moses Coulee. But when you look at it over a large enough area, you realize that area here is actually not really marking the furthest extent of the ice. It went further than that zone, and now we're in this eastern side of it where there are moraines. And we crossed the moraine on our way here to this parking area. I mean, did you see it on the way over?
No.
Yes.
I saw a couple of them. Yeah. Right at the intersection, we were actually cutting. The intersection cuts across the
more or less
the moraine.
The moraine is where the yellow sign is.
Yeah.
That hump in the distance, that's the moraine, or one of the moraines.
Right.
So where are we on the DEM, on the LiDAR? We are right. So we took this road. You can see the road really well. You climbed up. Some of you noticed that there's a bit of a gravel bar on the way up. As you drive over, you move onto the less. So far we were in the less. Not ice affected, not flood affected. A little strip, because the highway crosses, and we're onto this ridge here. We just turned and we crossed. So this lump that you see here is that hump in the distance. A little disappointing if you ask me. But that's what moraines look like, yeah.
In the continental ice sheet, is the moraine more zonal and different than a typical alpine moraine? Are they similar? But it's like most alpine moraines are, I mean, they're clear cut, right, with that hump and textbook, all that kind of
So
stuff.
there's two things that control. Moraines can be, like continental ice sheet moraines can be quite sharp. The reality is that there's also fluctuations of the ice in the terminal zone for different reasons. So when I talk about a zone or a complex of moraines, that's a bit of what we have too. The ice is advancing and retreating periodically. In an alpine system, you tend to see really sharp ones, in part because, and there's a transition to what we call lateral moraines. So the lateral to frontal or terminal moraine is much clearer and continuous in alpine systems, largely because in alpine systems, lateral moraines get their sediment from the sides of the valleys, that they kind of just, the talus that comes down that gets incorporated and gets moved. And in a continental ice sheet like this, we don't have giant hillsides that generate lots of talus. So the source of sediment to build the moraine is actually from the base of the ice, from the erosion, and from shearing of that basal ice towards the surface to sort of, if you've seen pictures of glaciers, in the, we call the ablation zone, the zone that's melting, there's a lot, that's pretty dirty. There's a lot of cover on the surface, and that's all the sediment that will be in part concentrated through shearing at the base. But also, because it's melting, there's water moving that sediment. So a moraine is not typically, especially these, they're not made of till per se. There's elements, there's a bit of till in it, but there's also a lot of sand and gravel and outwash and reworking. It's a mixed bag of sediment because it's just reflecting different processes.
How thick would the ice wall have been here at the end of all things?
Good. Not a wall for starters, right? So tapering, exactly. How thick? I don't know exactly. Their projection, well, I mean, basically on the other side of that intersection, 0, right? And then this way, thickening as we move, tens to hundreds of meters, but you know, it's a fairly low gradient ice sheet as far as, or lobe as far as people have been able to reconstruct. It's not a particularly steep one.
So it's not like the Ice Age cartoons.
No, it's just no squirrel with giant acorns and that stuff. Yeah.
And the fact that we're at the end, you would expect it to be moving, fluctuating more and more,
Yes.
depending on the.
And you would expect also that the effects of melting at the front would be felt more just because there's less ice to melt, right? So we release more sediment just close to the margin because there's just less to melt. What's that?
There'd be water coming underneath it through escapes
Absolutely,
coming
there
out,
would
so
be.
it could be a tremendous outflow.
So-
sometimes.
This is the furthest extent
Yeah.
that we can map. And if you look back this way, you'll see there's a series of these ridges. They're more or less parallel to each other. They're all nicely curved and arcuate, so that's reflecting the shape of the ice more or less. And there's this zone that kind of steps back. So these are also what we call recessional moraine. So as the ice is retreating, so when ice is retreating, there's still a flux of ice that's moving. So it's not like a rubber band that you pull to a certain location and you just spring it right back. The ice is still advancing, yet in the balance of how much ice is being brought in to how much you're melting at the front, the melting part is losing compared to the new ice being moving. So the glacier is still moving, yet the margin is stepping back or is retreating because we're melting more. And you're right that we should be producing lots of water as we melt the ice, and that water needs to go somewhere. So if you look at in here, you notice that there's lots of little flat areas on the landscape. We lose some of the incised and kind of gullied parts of the loess, and we've got these recessional moraines. We start to see bed forms that are aligned, like drumlins and other things like that, that are indicative of ice flow. But we're also probably ponding water between the moraines, temporary shallow little ponds. We see that in glacial areas all the time. So a lot of what we're standing on, we were talking about it being less, probably has a less origin, a source of less, but a good chance that it's also like little meltwater ponds that would have just had a lot of silt and clay in it, and now just sort of infill the topography into these flattish areas behind the moraines as we go. Yeah, Tom.
I noticed that very last moraine is just,
This one?
yeah, the very furthest moraine is just short of the Cooley monocline.
Yeah.
And I'm wondering, is the monocline forcing that water back in to cause all that erosion that's leading down into?
So let's move here because the Cooley monocline might be a bit more visible.
Yeah.
So there's the Cooley monocline sort of trends this way. This ridge probably is controlled by the monocline.
Right.
And in part, yeah, the ice might well be blocked somewhat topographically by the monocline, but we'll see elsewhere that probably the ice invaded into Grand Coulee. So the parts I was arm waving at the last stop, we can see them here. We were down here. We were talking about Steamboat Rock. This is right here. We were talking about the breach of the Grand Coulee. This is the critical piece here. And Northrop Canyon is this little strip here.
Right.
So less, no scabland, exposed basalt, somewhat developed scabland, but not very deep, but certainly smaller cataracts. They fit the pattern. And this is the idea of Lake Columbia starts basically just here. And so this is where you might be able to sneak a bit of water above a long Okanagan lobe,
Yes.
along the margin of the Okanagan lobe. So it requires that the lobe has moved into the Grand Coulee. And so that would explain how we get this moraine on the top of Steamboat. And it diverts water a little bit over here. But if you do that, that clearly is showing you that it was going into some kind of channel.
But there's undeformed loess on the east side of
On this side, absolutely.
on the east side of Steamboat.
Exactly.
Wow.
So if you're sneaking a little bit of water, I think the emphasis here is that it's a little bit of water, because that's got to go here, and there's a cataract, so it's draining into something already there. There's a depression, there's a low there, there's an outlet, essentially. There's an outlet there if you want to sneak it through here. Or it continued further, and we later the cataract retreated even more to breach. So that whole question of the breach is really critical in terms of its timing and how big it is. Our next stop, we'll talk about routing water into Moses Coulee, and one of the models that is proposed is that if the cataract is not breached, if there's enough rock cover over here at a certain time, then there's a pathway to get water flowing out of Lake Columbia along the margin of Okanagan Lobe and into Moses Coulee. That's one of the proposed ways of doing it.
Yeah.
If Grand Coulee is breached to 400, which is the elevation down here, much of these arguments just disappear. Like they don't work. It's game over for a lot of these arguments unless you can block the coulee with ice to allow Lake Columbia to pond. And what's clear from all the hydraulic modeling is that if the Grand Coulee is open, In other words, if it's been breached or not blocked by ice, you cannot, by dumping Missoula water into Lake Columbia and raising the stage, you cannot raise the Lake Columbia level, high enough to spill over. Grand Coulee acts like basically a siphon. There's no hydraulic scenario when you run with different amounts of water, different speeds and so forth, that allow you to raise water level high enough. Like, so there's a leak in your bathtub. It's not even a leak. There's a giant gaping hole in your bathtub. That's the Grand Coulee. And that hole is so big that there's no amount of water you can dump into the bathtub fast enough to raise the water surface high enough momentarily to spill over. The hole here, the breach, the siphon is too great. So if the Grand Coulee is open and you want to get water above that, you basically can't. Doesn't matter what the Okanagan lobe is doing to block the Columbia. If that passage is open, game over for anything overspilling. So once the Grand Coulee is open, that also means that you can't pass water through Cheney, Palouse, and Telford.
You can't?
You cannot, because as soon as you dump Missoula water into Lake Columbia, that siphon is too great. Like when I say siphon, I mean it's basically a hydraulic low that literally pulls water out. It's the bottom of your bathtub. Does that make sense for everybody? Mm-hmm. So this is a key part of the story in terms of the valve, if you want to think of it as a valve, of controlling the drainage and the directions in which scabland areas are affected at what time. So you want to get water in the Telford, Crab Creek, Cheney, Palouse area, this has to be closed, either by rock or by ice or a combo of the two.
So, but getting back to the LiDAR,
Yeah.
you've got that massive scabland area just
Here.
just there,
Yeah.
where it looks like a lot of water is coming from the east.
Yeah.
But is that water that's just came out of the glacier and couldn't get past the Coulee monocline, so it was pushed back toward Moses Coulee?
So
A lot of water went there.
a lot of water went through there, absolutely. So this is one of the interesting parts of the moraine part, is that when you actually go and walk the ground in the area that's usually mapped as the moraine, the actual moraine part, which would be kind of a deposit of sediment, is in fact not a deposit area, it's an erosional area, which is this. It's the zone, it's the terminal zone, so we're okay with the idea that the moraine is the terminal zone, but it is not marked in this case, in this location, by a major deposit of sediment. It's actually marked by a major zone of excavation and erosion. So Tom's right that this is all in basalt. This is kind of a scabby looking area, scabland area. And there's been probably at least 2 different rounds of water flow through there. A subglacial component, which we'll talk about at the next stop, but also a subaerial one, like outwash in front of the ice, that reutilizes some of these. So when what we'll see is that many of these are eroded, and then there's some sand and gravel deposits, basically an outwash train that makes its way through this bit of a maze of scabland areas. But we've dissected scabland surfaces, bedrock, basalt surfaces, to create that pattern through here.
Now, I know the other map also does a good job of showing you how the terminal end of the upper Grand Coulee gives a lot of room to spread out for the water.
In here, in the upper part.
No, at the terminal end of the upper Grand Coulee. That's where the water can spread out so much.
In here, you mean? Yeah.
Yeah.
Yeah. In terms of excavating a broad area, you mean?
Right.
And then focusing into. Yeah, I see what you mean. Yeah, absolutely.
Is that the Heartline expansion bar? Is that what it's called?
Yeah, a bit further, the Heartline Basin.
Yeah.
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 Exactly. We passed it, didn't point it out, but it was on the right-hand side. Is a big flat grassy area, a big bar in the Heartline.
Why don't we see glacial outwash streams here?
That's a great question. Like that would be, if we have ice and we have the moraines showing us ice, and we have recessional moraines, you only receive the moraines, there's meltwater being produced. So what are the options? Didn't produce that much. Or you'd expect, in fact, that there was some, and I wouldn't be surprised if some of these sort of larger gullies might, in fact, be a bit of outwash that went there. But the other thing to think about is that the lobe that moved through here and the size of the moraine suggests that it wasn't massively erosive. And so the ice was probably pretty thin. You can get ice to move across the Waterville Plateau if the bed is particularly wet and slippery. So you don't end up with a lot of ice, great thickness of ice that's very erosive. And it's moving over a blanket or less. And so the sediment that it's going to release, as with meltwater, is going to be less. It's going to be silt. And so we're not going to see enormous amounts of giant boulders. There are a few big haystack boulders. In fact, there's one on the highway that we'll see across the road. There's a few here and there. You can actually see them on the LiDAR. They're here on the dots here, and a bit beyond there. These are big haystack boulders, or they're piles of boulders that the farmers have pulled out of the fields, but there's a large amount of less. So we may not see our classic braided gravel sand outwash surface because we're not moving a lot of sand and gravel. The ice is moving over less. It's not very erosive, and it just melts, not in very large quantities here, and so it's not mobilizing tremendous amounts of really coarse sediment, just because it's not sourcing any.
With respect to those recessional moraines,
Yeah.
even I can see 1, 2, 3,
Absolutely.
4. So could you work? Those each represent a still stand in
Yes.
the climate, right? You're warming, you flatten out for a while. You warm, you flatten out. Could you take that pattern and go to tree rings or Greenland ice or something like that, and start to get dates using that pattern?
So they record yes, there's a climatic signal, but I think it's probably too rapid, and it might be too localized. So what we're really looking at here are combinations of seasons, maybe even decadal sets of seasons, where there's a bit more mass being transferred down and a bit less, and it's melting, or 1 year's a bit warmer, and so there's a bit more retreat and a bit more re-advance after.
Okay.
So it's probably handfuls of seasons to maybe centuries max that control those recessional moraines.
Okay.
And this is happening as the ice is retreating, right? So the ice is going to be stepping back northward. It's going to do this in a couple thousand years. We'll talk about dates at the next stop. So a couple thousand years is relatively, if you look at the distance it covers, and we keep things simple, it's retreating at about the same rate as we see glaciers retreating today.
So
That's
what about farther north? Are there more recessional
Yeah.
moraines up
There's recessional moraines that continue all the way. They're not so visible on this LiDAR because of the resolution. A few of them are. I mean, I've mapped a few. There's pink lines in here, but they continue. They're up here as well. So there's a fairly systematic pattern of these arcuate moraines, which tells us a lot about how the ice is actually behaving. So it means that the ice is not. It's actively retreating. So when we think about glaciers that reach a terminus, some glaciers stagnate. In other words, they're too thin to move, and they're not sufficiently connected to their source areas anymore to move. So they just basically become stagnant in place, and they just decay in place. You get kettles, you get all sorts of different landforms and sediments that are there. The fact that we see so many recessional moraines tells us that the ice was still very much connected to source areas to have this flux of ice, yet we had a seasonal melting that was outpacing the inflow of ice. So this is what we call active retreat. In other words, the glacier is still operating and moving, and yet it's retreating. Okay? So those recessional moraines tell us, is that me? No. Tells us that these are retreating quite actively. And then what we also see, we won't see too many on here, but there's a bunch of eskers. And eskers tell us about water production, and the eskers, many of them terminate at the moraines. So eskers are formed in conduits under the ice, and they come out at the front of the ice. So we got a moraine marking the front of the ice, and we've got an esker that basically is the plumbing that allowed sediment to move under the ice and come out at the moraine.
and it ends right at the moraine?
Pretty close, yeah. And often on the other side of the moraine, there's almost like a little delta. So it's like the flow expands at the ice margin, and sometimes probably it was ponded, so you see nice little channels.
You can still see that?
Oh yeah, you can see them.
The green lines are eskers.
You don't even need, the green lines are some of the eskers, but there's lots of eskers. You can see them on, this is the same image. Here. There's a couple of spots. Let me find them again.
Can you hold it up high?
Yeah, I just need to find it first. Yeah, so right here, there's a great one at a place called Sims Corner. There's an esker ridge right here, the nice snaky little ridge you have here. There's a couple others here that terminate at little deltas. So that's
You can still see the deltas.
you see the deltas super well. Yeah, you see the channels on the top of the delta, like the expansion and the flow. Yeah, it's beautiful, and they're small.
Themselves are
Eh?
subtle on the landscape.
They are.
When you're driving across them, whatever, it's almost hard to tell whether
Yeah.
this is the esker or just another one of the little moraines.
Totally.
They're subtle.
Yeah. This is where the LiDAR is just such a boon, because those questions there's no ambiguity about what they are, or more often than not, there isn't too much. Yeah.
What are these patterns? It looks like ripples almost.
Yes, they are. There's a whole train of these sort of sharp ridges that are short. They resemble, there's a term in glacial geology called Daguerre moraines, if you're familiar with that. Daguerre moraine, they're basically in an area of usually ponded water. It can be shallow or deep. The base of the ice has crevasses, and there's sediment being squeezed into the crevasses at the base of the ice. So this is essentially, if that's what they are, and they sure look the part, they are basically the pattern of the infilled basal crevasses of the ice in this area, and terminating at a moraine here. So imagine ice, highly fractured, crevassed ice kind of breaking up, and then there's some squeezing of the sediment in some of these.
Do you know why this area is so flat? Like
That's a lake.
It's a lake.
That's a lake today.
oh, it's a lake.
It's a lake. It's a reservoir. Yeah, it's dammed right here by this feature.
Lake, right?
Banks Lake. Yeah.
There was no wind that day, so
Totally flat.
no waves.
So, moraine, just to get our heads around the idea of what a moraine looks like, and these are the furthest extent of the ice, but then we're going to move into the area that most people think of with the Withrow moraine, which is really the Withrow terminal zone, because there's not much evidence of a moraine. Perhaps this pile of sediment here that's irregular, that's the best candidate for calling that moraine material. But once we move into to Moses Coulee, pardon me, it's going to be a totally different landscape. We're in a flood cataract with big bars, big flows, and we'll talk about how this connects to that and beyond. Okay? So if you've never done this drive from this point, we're going to double back, hang a right on Highway 2. So we're going to return to this long straight road, and then we're going to come down this long grade into Moses Coulee. It's spectacular, period. Like, I'm not a very spiritual person, but I have near religious experiences when I go to Moses Coulee. It's been a special place. Like, Native Americans consider this place is a sacred place for Native Americans, and there are stories upon stories upon stories of activity in Moses Coulee. It's just one of those places that has energy, and you got to be in there to really feel it. So I hope you feel it today, because every time I get in there, I'm feeling it. And
Why is only this area scabby and
you're too fast for us. We got to hold on. We'll get there. I'll answer your questions. So after you get the feeling of Moses Coulee, as you come down the grade, we're going to turn and drive this way. But as you're coming down and you see the coulee, the highway you'll see in the distance rises, and it's going to rise up a gradual hill. It's this feature, and we'll talk about it more. This is a big flood bar in Moses Coulee. It looks totally different from the floor of the coulee, from the sides of the coulee, because that's basalt, from the uplands that are less. This is a gravel pile. It's a flood feature. It's there because there's a bit of bedrock sticking out, and just appreciate the size of it, because it is massive. It is massive, and these bars are really, really important to how we think about the quantities of water, the volumes that move through, and the energy that they have as they come through. So bars are one of the key indicators, landforms, clues we use to reconstruct discharge magnitudes and the stories around Moses Coulee. But yeah, Moses Coulee, I'm glad we can go there on a good day like today, because it's a great place. It's a great, great place if you've never been. And then after we've gone there, we'll drive down the coulee. We'll spend the rest of the day driving down the coulee. So you'll get the full Moses experience today.